I want to look at this question now. Pause the video and give it a crack. Assuming you had a go now, we'll start with the answer. First, we'll find the areas of the steels and aluminum. So area of steel is pi over 4, 25 millimeters squared, which roughly is 490.9 millimeters squared. And the area of aluminum is pi over 4, 50 squared, which is roughly 1963 millimeter squared. Okay, now let's do some statics. We know at the end the system will be under stress, and the only way this can be under stress is that the aluminum pushes upwards, causing steel to be in tension, try to pull things back. We know that the temperature is rising, which means everything is expanding, and this is the only way stress can be caused in the system. Otherwise, you have to decrease temperatures so that aluminum is under tension, which doesn't really work. So this is stress in steel and the stress in aluminum, and this is acting on bar ACE. So from this, we know sigma y will be equal to 0, which is twice PS plus PA. Sorry, let's define a coordinate direction. So we'll call that y in the positive direction. So it will be actually negative 2 PS plus 1 PA. And this is equivalent to saying PA is twice PS. We'll call that equation 1. Now, we'll have to assume that one of the members yields first than the other. And flipping the coin, I'm going to say steel yields first. How I will check if steel actually yields first is I'll find PS by assuming it's at its yielding point. So what I'm doing here is basically Hooke's law, which says stress is equal to force over area. If I just move area to the other side, I get force left alone. So this allows me to find that PS is 169,351 newtons. That's the same thing as saying 169.4 kilonewtons. Now we'll plug this back in the aluminum to see whether aluminum yields. If it doesn't, that means steel will yield first. So sigma of aluminum is equal to 2 PS from equation 1 over the area of aluminum, which is equal to twice 169,351 over 1963, That's in newtons, millimeter squared. And we'll find supposedly the stress in aluminum is, hold on, let's plug that into the calculator. 69351 over 1963. And we'll get aluminum has a stress of 172.54 megapascal, which is lower than the yielding stress of aluminum. Thus, assumption was correct. Cool. Now we can proceed to deformation analysis. We'll draw the free body diagram again, but this time we'll try it more completely. That's the rigid bar. And we have that's a terrible drawing. A bar of aluminum, 2 bars of steel. And in white, we're drawing the initial state after temperature has risen. Everything will have shifted upwards, which means steel in tension has gone up, and aluminum in compression, without the influence of the compression on the rigid member, it would be larger or longer in distance and be compressed down to the equilibrium position. This means, let me get my white color back. The original length of steel plus deformation elongation of steel is equal to equilibrium length. Let's label that A, S. And then we can say the original length of aluminum minus the deformation of stress is equal to, actually no, it's more complicated than that. We have to add a term of thermal expansion to both sides. So now we can say that's the equilibrium length. Now we can equate these two equations. Okay, what is the original length of steel? I know it's probably, you're going to say 400, but in this case, it's actually the length that is between the rigid bars. So originally, it's 300.1, and the original aluminum length was 300 exactly. That means 300.1 plus all the other terms is equal to 300 minus and plus all the other terms. We can get rid of 300 on both sides, so we're left with 0.1 plus sigma delta S plus delta TS. And let's switch these terms around. So you get delta TA minus delta A. And this is our deformation relation, and we'll call that equation 2. Now we can plug in the delta P relation into each of these deltas, and I can say 0.1 plus PS LS over AS ES plus alpha S delta T. Actually, no, let's write delta T last. LS delta T is equal to PA LA over AA EA minus, wait, I did that backwards. Whoops. Okay, thermal, it was alpha A LA delta T. There you go. Let's fix my L a little bit. It looks like a smaller L. Good enough. We know previously that PA is just twice PS. So the only unknown we have here is delta T, which is the rise in temperature. So we can plug in some numbers here. 0.1 remains, and PS was 169.4 kilopascal. The length of steel is 400. Let's double check if it's actually 400. Yeah, cool. It's 400 over AS. It was 490.9. And finally E. This is 200 gigapascal. So I have kilonewtons here along with gigapascal and millimeters all around. This together should give me millimeters. Now, third term, we have 24 times 10 to the negative 6. Wait, no. This is 12 times 6, 10 to the negative 6 per degree C. And the length of steel, again, is 400 multiplied by delta T. That is equal to 24 times 10 to the negative 6 times 300 millimeters delta T. Finally, minus twice 169.4 kilonewtons, 300 millimeter length over 1963 millimeters squared multiplied by 68.9 gigapascal. Okay, now we can convert some more numbers. So that is 0.1 plus 0.69 plus, let's plug that into the calculator again. 10 to the power of negative 6 multiply 400. That is 0.0048 delta T. On the other side, it would be double that. No, it would be 24 times 10 to the negative 6 times 300, which gives you 0.0072 delta T minus 0.751 millimeters. Okay, then let's arrange the sides so we have all the constants in one side and the unknown on the other. Okay, 0.0072 minus 0.0048 in brackets delta t. Okay, let's plug that into the calculator and find delta t. 0.1 plus 0.69 plus 0.751 over 0.0072 minus 0.0048, and I get a temperature of 642 degrees Celsius. Now note, this is the change in temperature. We are asked to find the temperature that it needs to reach. We know the ambient temperature was 30 degrees Celsius. Then we add on the rising temperature, and it will give you the final temperature. The final temperature will be equal to 672 degrees Celsius. And this is the answer.